what happened when people move to cities is people are shaping cities. There are new construction everywhere, and there are also gentrification everywhere. If you search for information on urban transformation on Google, all these news articles will pop out, like social and economic changes benefiting some groups while displacing others. At the same time, global temperature have increased over 1.1 Celsius degrees since the pre-industrial times. And this means
to close those boxes.
Yeah, for sure.
I think predict that okay. And
Click that for something. Yeah.
north,
I think if you exit the presenter view, maybe it'll be to close that. I mean, exit the Zoom sharing,
Okay.
then you see a box, and then
Oh, nice.
then come back here.
Okay.
and you also need to share some part is the share. Part.
Okay. Yeah.
Yeah, correct.
Yeah, so at the same time, our climate is changing. This is the diagram of the number of extreme events happening in the last 40 years in the US. The number of this $1 billion disaster has nearly tripled in the last 40 years. Yeah, and these climate events are also shaping cities. We witnessed, like, in the last few years, Hurricane Helene and Hurricane Milton destroyed a lot of neighborhoods. And the way the community rebuilds after those events actually have a profound influence on the social and physical landscape of cities. So our cities are changing profoundly. Human migration, gentrification, extreme weather, and all kinds of different policy. But how do we understand, like, for those research questions, what are the specific drivers for those change? Like, is my neighborhood gentrifying? Or is there any spread of informal settlements? How many buildings are renovated? How many buildings are demolished? Have the damaged buildings actually been rebuilt? What buildings have the roof, like, foundational upgrades? Are they upgraded? To answer these questions, building data is very important, especially on the building level. And for those building level data, we need to monitor reconstruction, abandonment, maintenance upgrades, and also we can have some insights on the structural quality of these buildings, resilience to the extreme weathers, and their efficiency. But the challenge is those building level data are very hard to collect and very costly. So how to collect those data? Right now, we kind of rely on a few different sources. There are these national level census happens every 10 years. And also the American Community Survey happen every 1 to 5 years. And some metropolitan like Seattle, New York City, Chicago, those large cities, they have their own data hub. They sometimes publish their construction permits on public safety, transportation, public health. And also some utility company like PG&E, Southern California Edison, they publish their energy consumption data. But those data are mostly not timely updated. And when they are available, in a lot of times they have pretty low spatial granularity and it's very costly. And most importantly, they're kind of data silos between each other, especially if you want to do research across regions, like large scale. Sometimes their formats are not compatible, and it's very hard to answer a research question at a large scale. So we're looking to opportunities, like how can we have this large scale, but also granular data? The first thing we find is satellite data. Satellite data are becoming more affordable, more available, like companies like Planet Labs, they have this daily refreshed satellite data, and the marginal cost of launching a satellite into space is going down, like drop dramatically. And like here's example of like the Sentinel satellites from the ESA and showing how they revisit the same spots like every 5 days. We can track the buildings and the landscapes change. And the other opportunity is street view data is also becoming more widely available. Google collects street views starting from 2007. And in major cities like San Francisco, they actually updated 1 to 2 times per year. It is very convenient. And they have a static street view API for us to download those data. So we can not only see the most updated street view, but also the historical street views. Okay. And on the method side, machine learning and AI are becoming more available too. So we have this huge amount of neural networks methods coming up every year, like CNN like a couple of years back, and then vision transformers, and now like vision language models. And we have all these domain features from a lot of AI papers on how to do classification, detection, segmentation on all the remote sensing data. But the challenge is we still don't have like a pre-trained, very large change detection model. And those methods can susceptible to noisy signals. And they are limited in their inference time. That's a couple of challenges we find when we start our work. Okay, to summarize the research gap. So first of all, we need an understanding how cities change over time due to factors like extreme weather and gentrification and human migration. But we don't have that building level data. So we have this data gap. To get this data, we need this existing methods to be more versatile and efficient. So I will introduce the work we're doing for the last couple of years. First, from the machine learning toolbox on the remote sensing data, like satellite data, like street views, and then 2 applications, one on climate resilience and the other one on gentrification. And the work we've done spanned from like 2021 to 2024, in that window. So I'll first introduce the toolbox. Yeah, the first task we start to look at is actually change detection. A very simple question is, for a building, if we have 2 images in time I and time j, how do we know that if there's a new construction or not? Very simple classification problems. And when we search online, like what are the open source state-of-the-art change detection model? Can we just directly apply it on street images? And when we do that, we find that the results are not that promising. So we have to somehow clear out labels and clear out training data to train a model that can do this task well. Like this is around 22, 23. I think at that time, like all the large language models have not been popular yet. So we still have to train this like specified change detection model. And we reach like a pretty decent accuracy. And once we have this model, we apply it on a larger scale. And we collect those review data for these few cities, Seattle, SF, Oakland, LA, Boston. And we publish this data set called City Pulse. It's like a change detection street view data sets. And at that time, it's the largest open source data set, like tracking the change of buildings. And some previous work, they only track like one city in like after tsunami or after nature disaster, but we are kind of doing a multi-city, multi-year approach. And our model will be able to like detect whether there's a new building there or there's like the change is not significant. Sometimes the model has to able to distinguish the noisy signals like the angle difference or the weather are different between different years. And they need to know like focus, those red pixels are the model's attention. So they basically pay more attention to the building instead of the noisy environments. And once we do the building level classification, we want to move a level beyond to the neighborhood level. So if we know, like for a neighborhood, how many buildings are being renovated, we actually can classify this neighborhood as whether they're being gentrified. So this is like another study we did to aggregate this building level results to the neighborhood level. So we can see each neighborhood as a container of maybe a couple hundred. For a large neighborhood, maybe a couple of thousand buildings, and for each building, we have a classification. And then we aggregate this classification to this neighborhood level to classify each neighborhood as gentrifying or not gentrifying with an attention. Attention is like a weighted sum for those building level results. And yeah, so our baseline is like a heuristic approach to determine gentrification. And our approach was able to filter out noisy signals like those buildings that are not very visible. The attention, we just gave them a lower weight. And yeah, so those are the two studies to like model level work we did on the building level and on the neighborhood level. And around 23, 24-ish, we see this, like, I think ChatGPT was introduced end of 22. And beginning of 23, we see some open source large language model and vision language model began to develop very quickly. And we realized one thing, that instead of just training a model to do one task, those vision language models are actually pretty powerful in the open world, open knowledge. You can just ask the model if there's a construction, and the model can already give you a pretty good answer. So instead of training like 4 separate models for those 4 separate tasks, what if we somehow consolidate them into a large vision language model? And at that time, those are the 3 state-of-the-art vision language model, the GPT-4o, Gemini 1.5, and Llama 3. It's around 23, 24. And when we directly apply them on the remote sensing data on buildings, on the built environment, we find that they have these 2 limitations, the accuracy and the scalability. So remote sensing data are unique, that they cannot be associated with those task descriptions like at very large scale from the internet. So this first few versions of this large language model, they are trained on this huge internet corpus, but they somehow don't have enough. I think they don't have enough remote sensing data in their pre-training stage. So when we first asked this model, like, what is this image? For example, like a top-down view of a school, like maybe UC-Berkeley, and the model doesn't have the capacity to give you a very accurate answer. And also it's limited scalability, like each image have to go through their API, and it's very costly at that time. I believe the cost has gone down over the years. And yeah, so we think that we need to provide a large scale remote sensing multi-model data to train this vision language model, and also somehow make it more scalable, like the multi-model encoder. That's how we start this study called SkyScript. We want to somehow extract all this geospatial data at a very large scale. How do we do that? We have actually 2 main sources. For image, we use Google Earth Engine. And for this language, we use OpenStreetMap. So OpenStreetMap is actually an open source map version of Google Maps. They have all the points of interest, POIs, and they have this categories, classifications of a place. For example, if you located with the coordinates and gave them like a radius of 20 miles, they can give you this, return this like land use farmland, crop, cotton, like those tags for this place. And it's almost like an internet for the physical world. And we somehow, at that time, we find that it's actually very convenient to use to actually match to those remote sensing images from Google Earth. So we know that this contextual like language descriptions of an image instead of just 1 or 2 words. And we look at all the previous open source remote sensing data. Many of them are in a huge quantity, like in the order of millions. But one of the limitations is they don't have enough distinct like tags and labels. Many of them have less than 100 labels, say whether there's a building, whether there's a school, like airport, those type of very straightforward classification labels. And so since like we can leverage all this open knowledge of large language models, we can download way more tags and labels with like OpenStreetMap. So we actually have more than 10,000 different tags. Yeah, and we do some benchmark with the CLIP model. So CLIP is an open source model from OpenAI that actually align language and vision. They try to minimize the distance between like images and text tokens that have similar semantic meanings. And we kind of use their checkpoint and training another CLIP model with skyscraper data, and we'll be able to improve like those remote sensing tags on top of it.
Just to clarify, SkyScript is one data source
Yes.
available?
Yes, so it's an open source data.
It's open source.
Yes, we open
Okay.
source on GitHub. It has around a couple million
And
images.
it's to understand correctly, you have Google Earth data and OSM
Yes,
POI data.
yes,
Both, okay.
yes.
But Google Earth is not free, it's not open source.
Yeah, so for academic use, I
Okay.
believe they can be shared. I think we have the script to download those data on GitHub. Yes. Street View is a little bit strict. It's more strict.
What is the difference between a SkyScript and what you are proposing?
Yeah, so skyscraper is what we are proposing.
That's what I wanted to
Yeah, yeah,
understand. Okay. perfect.
Yes.
Yes.
It's our data sets. Yeah, so another task we think that on top of skyscripts, so this is our ongoing work we still haven't submitted. Can we do something like an instruction tuning? Like give the model like an instruction, like find like given these two examples, find the residential buildings with well-maintained greenery. Maybe give them a couple hundred examples. Can we do a supervised fine tuning on a large vision language model? And yeah, so this is another approach. So instead of just building on top of SkyScript, which is a large data sets with all the tags on the images, can we add another layer of chain of thoughts on top of it? Yeah, so some preliminary, I'll skip it since it's ongoing work. Yeah, so this is the machine learning toolbox we developed over the years, like doing change detection works and doing all this semantic understanding at large scale with open world knowledge. Now we're move forward to an application study we did for monitoring how building recovered from extreme weather. So it was under review at the time I graduated, but we're very excited that it was accepted, I think, last August in Nature. It took us a year, like all this review process. We had 4 reviewers, and one of them asked us basically to recollect all the building data to validate that our street view data are not biased. Like, so we spent a lot of time rebuttaling that paper. Yeah, I'm happy to introduce that paper. So this is the motivation. We are working with Rom and Professor Tianyuan Huang from the sociology department at Stanford. And it's a very interdisciplinary study. So we kind of brainstorm how much can we do, like from the street view data to go a step beyond, say, this building is newly constructed or demolished. What kind of social dynamics or what kind of insights can we generate from our technology? And we find that in this disaster recovery community, there are actually 2 competing theories on how neighborhoods recover after extreme events. There's this segmented withdrawal hypothesis, which assumes that like more affluent population will be moving out of these damaged zones while more vulnerable population will stay, like after extreme weather. And there's another hypothesis called recovery machine says the advantaged groups actually will stay, but the vulnerable group will be squeezed out. It's very interesting, like those are actually on the opposite side of each other. And sometimes people observe this trend in like different nature disaster. And we think Street View is a perfect tool to actually monitor this change. So we start to look.
Sorry,
Yeah.
can I ask, how do you define advantaged?
We kind of just categorize by income. Like there's higher income, middle income, and lower income, with the buckets by the US Census. Yeah,
So advantage is only high or high middle or
yeah, it's more like high income, higher.
Only
income
high.
neighborhoods. Yes,
And that's a block level statistics instead of a household level.
yeah, that's a block level statistics, exactly. From the US Census and CS. Yeah, so we start to look into data and we find one data source very convenient from FEMA is this historical damage assessment data. FEMA actually recorded in the last 50 years, the most severe nature disaster, like those are the dozen of billion-dollar disasters hitting the coastal region of the US. Most of them are hurricanes and floodings, and they actually published the building level data on how on like for all those damaged buildings, the household sometimes apply for a FEMA grants to rebuild. So FEMA track those applications, and they publish those data in their websites. I think it's called Open FEMA something data, and they have around 700,000 street view images. Oh, sorry, they have around 118,000 buildings, and we've been able to download like for each building around 5 to 8 street view images. So in total, we have less than 1 million street view images. And across 23 states and more than 2,000 census tracts. Yeah, and we find very interesting that we can use Street View to monitor how buildings change over time after disaster. And the above example is a building in Houston. And after Hurricane Harvey, you can see the building is completely demolished and it turns into a lawn actually. And the second example here is a building after Hurricane Sandy in New York. And the building get rebuilt after a couple of years. And it turns into a more resilient, a higher structure, more well-maintained structure. And with this data, it's actually very convenient for us to generate insights on how building recover, like after all these events. And we're able to map this at scale. So for all this building data from FEMA, we track their street views and map how much of them are being abandoned and how much of them have been improved. And this is like a map of them. You can see some regional disparities actually. In northeastern regions such as New York, New Jersey, and Connecticut, you have a substantially lower portion of abandoned buildings and higher portion of improved buildings, with actually less than 20% of them being abandoned and more than 80% of them are being rebuilt. But in contrast, southeastern Texas, southern Louisiana, and Mississippi, those states which are experienced multiple hurricanes over the years, have more than 50% of affected buildings left abandoned, and fewer than 40% are being rebuilt.
So what you're categorizing here is actually just rebuilt or not rebuilt,
Yeah, it's like
is that right?
for each neighborhood. So this is the county level map. So each county, we have the percentage of damaged buildings that are being rebuilt, and percentage of damaged buildings that are being abandoned. So those are the two matrix we're visualizing here.
Okay.
Yes.
Yeah, because I'm just thinking, maybe the structure is rebuilt, but it was abandoned by the previous owners because they cannot afford to rebuild. And then you have some other entity that, you know, finds a way to purchase it and.
Yes.
And buys it.
Yeah, exactly. So that was actually the limitation of our study. We don't track how the human, like the homeowner migrate or not. We kind of track how the built environment change over time in this place. So the assumption is if we can track the street view, we can actually see how the building changed, but without survey or without actually field survey.
Could you not use real estate records and see if there was a transaction on the parcel?
It's available in like big cities like Houston, but it's not very available in suburban areas. So it's hard to do that study at this scale.
Really?
Yeah. Yeah. We tried that. We try to find construction permits with maybe
There
homeowners
is a data set called Atom, ATTON, that
have all the
all the
transactions.
US, yes.
I see. Yeah, we didn't look into that. So we try to like scope out projects in the building environments. It's like street view. It's
But in the two hypotheses you had before, is it implied that if you rebuild, probably it's gentrified?
Mhm.
And if it's abandoned, and yes.
Yeah.
And I'm sorry if I missed this, but is improvement just rebuild or is it like rebuild and it's like better?
Yeah, great question. So it's rebuilt and improved.
Okay.
Actually, there are sometimes people just rebuild their homes, but it's almost the same with their pre-disaster home.
How do you detect better?
Exactly. So we actually manually labeled around 1,000, less than 1,000 buildings. And we go through them like by us, like we label them, this is the same level pre-disaster, post-disaster. This is a better level post-disaster, or this is a lower level post-disaster. We have these three categories, like quantitatively categorize how buildings changed. And we kind of benchmark these models on our label set. It has around like 90% accuracy in determining whether the building have been abandoned and 80% accuracy in like classifying whether the building was being improved or like around the same level as pre-disaster.
What is the ground truth data? Sorry, this is like very
Yeah.
personal to me for a reason I might say, but
Yeah,
what is the ground truth data?
yeah, the ground truth is human labels from us. Yeah,
Oh, so.
so for example,
Okay,
here.
so you're human, because if they rebuild to what looks like the same building as before,
Yeah.
and say the original building is like 40 years old,
Mhm.
it may look the same on the outside,
Exactly.
but it may in fact be, you know, for a number of reasons, including higher building code and standards, you know, actually an improved building, so the assessed value ultimately would be higher.
Mhm.
You
Yeah,
know, so you can literally quantify it by the assessed value from accounting.
yeah,
So it seems to me even rebuilt to what looks like the same from the street
mhm.
is improved. Is it-
Yeah, so that is one way. The other way, it's like this visually a measurement of built environment, which we cannot see here. And in many counties, like New York, they have a code to actually require you to lift the foundation after the building is severely damaged after flooding.
Hmm.
And we can actually very accurately track that in street views. I have some examples. If the building remained the same pre and post, we kind of assume that the built environment, the building itself, kind of on the same level from street views. Yeah. Yeah. Yeah, so this is like one of the charts. We draw a conclusion here is the very stunning disparities between lower income, middle income, and higher income. Like for the higher income neighborhoods across country, across all these events, they have a very high probability of improvements. And for lower income neighborhoods, they have a much higher probability of building turned into abandonment. Yeah, and then so actually Ron pushed me to think, okay, we observe this trends, how could we model this recovery? And one of the papers he referenced is from this very classic disruption modeling for like electricity disruption. And they model this as like a curve where after the disruption, the performance will drop sharply. And then in the recovery curve, there's like partial recovery or full recovery. And sometimes it's taking longer than expected, sometimes it's taking faster. They have a time window to measure that. And can we actually like use the heuristics to apply that to neighborhood recovery? So we have this very easy like pencil dropped formula to calculate the score of recovery for each neighborhoods. So if a building is completely destroyed, we minus 1 point for that neighborhoods. And if the buildings still remain abandoned, we don't add anything. We keep the same amount. If the building is rebuilt to the same level, like visually, we add 1 point. So it's like -1 add 1 is the same. And if it's improved, we use this 1.3 like 30% increase. We have like this is after looking at like a few hundred examples. We use this as like predetermined measurements for this improvement, like 30%. So then we can draw this diagram. So like after disaster, how much of the buildings are being destroyed? And then how much of them are being improved or being abandoned can reflect it on the building, on neighborhood level. And this diagram will show like years after disaster, whether the neighborhoods recover to their pre-disaster status. And you can see higher income neighborhoods, they gradually return, and middle income, lower income, they kind of lag behind, and the disparity of them actually will increase after years of recovery.
And the data was a street view, no, FEMA data.
Yes, yeah.
All it's great data.
Yes,
And what is the geographic scope of this again? And what
yes.
are,
So the geographic scope is across around 20 states. And in the last 15 events.
So the yellow regions.
Yes, the yellow region. This actually, it's a graph from FEMA. We copy them here. And they have this open data sets for the last $15 billion disasters. Yeah,
Glenn, what,
yeah, please.
oh no, go ahead to that.
Yeah.
So. The one that you were just on, says they needed a piece of vocabulary from, oh yeah, what's the how big is the neighborhood?
Yeah, so here I believe this chart is census tract.
Okay,
Yes. So we have around less than 2,000 census tracts in total.
Do you first categorize for each household or each building the census tract and you somehow aggregate it or you
Yeah.
just, oh, I see.
Yeah, we aggregate it to the census tract level. And I believe higher income, meaning income, the average household income larger than $80,000. Middle income is between $40,000 to $80,000, and lower income is below $40,000 per year in our calculations.
Does this income compared within the state or just countrywide?
Yeah, country,
I
it's like
see.
absolute, yeah.
So like, maybe all counties in Massachusetts, they are upper income.
Yeah, that's possible. Yeah.
I see.
Yeah, so a lot of previous work, they use satellite imagery to measure how large is the damage. Like after the tsunami in Japan, there are a lot of remote sensing researchers, they publish how much of the cities are being destroyed, but very few studies, they cover this long period of disaster recovery. I think Street View can be a great tool to do that. Okay, after all this modeling and we know how badly our neighborhoods is damaged, we want to go a step even further to see what are the policy frameworks to actually help the neighborhoods recover. Those are the two main sources, the homeowner insurance and housing assistance programs. The insurance cost varies a lot between neighborhoods, and they can cover you a huge chunk of like recovery cost. And FEMA offered this assistance program with a few thousand to max like 41K dollars of assistance. And they prioritize the uninsured and underinsured homes. We first try to visualize what like how much homeowners are being insured. Like FEMA actually generously published this data set also. And like with our hypothesis, higher income, they definitely are covered, like more well covered by insurance. And this validates our hypothesis where almost 90%, 90+% of higher income homes are being home insured, but less around 15% on average. And for neighborhoods that are in lower income are covered by homeowner insurance, and similar trends for flood insurance. And we do this.
Just on that last one, is there a chance that there's some sort of bias in that the, I'm not quite sure how it works for the FEMA assistance that it, so there's only percent of FEMA assistance recipients, right? But if you are higher income, you are more likely to be savvy about being able to take advantage of FEMA assistance, whereas if you're low income, you're taking care of a bunch of kids and your parents. You're managing 3 jobs. You just can't sort out the bureaucracy of
exactly
taking advantage. Is that an issue here, or?
So this is home insurance coverage, and we have a assistant coverage plot here. Actually, it's actually validate your hypothesis. So those FEMA assistance, they're supposed to prioritize lower income neighborhoods, but it turns out higher income neighborhoods have a higher success rate when they apply for those grants. So
Okay.
there may be an information gap, like for lower income neighborhoods, they maybe don't have enough preparation when they file for applications, or they just don't do the application as often.
Right.
Yeah.
Okay, I see. I just anticipated what you were going to say later. Okay.
Exactly. So, and we try to correlate, and this is like a local correlation, not called correlation, like with the detected abandonment rate and improvement rate for neighborhoods, we find that insurance actually quite correlated. So if a neighborhood is more well insured, they're less likely to improve and they're more likely to improve and less likely to be abandoned. And for the FEMA assistance, we didn't observe like a very strong correlations. Partly because the system money is just not enough. They have a cap, like the maximum money that you can get from FEMA is like 41,000 in 2023. And it's like a small portion of the home cost compared with insurance payouts. Yeah, so we have 2 takeaways. One is like to answer our motivation, to answer the first competing hypothesis, our observations are more kind of support the discovery machine hypothesis, where there's increased disparities after the disaster, like on the built environment perspective. In this perspective, the higher income neighborhoods will be more likely to improve, and vulnerable like neighborhoods, their built environments tends to fade away. And for the policy side, we suggest homeowners in vulnerable communities, they have some support for like insurance. We noticed that the insurance money for insurance cost for those like very like high risk, high climate risk areas are actually increasing a lot, like really a lot. For a home in Oklahoma or in Louisiana, you can easily get to more than $10,000 per year. And there need to be some sort of assistance or design to better facilitate that. Otherwise, less people will be likely to afford it. And it turns out that those places were more likely to be abandoned. Yeah, I think that's the main like pieces of research I try to share today. I'm happy to answer any questions.
You have any skip the section?
Yeah, I think we have enough time, and that was like we briefly talked about it in the first section. Yeah,
Yes, if you just want to quickly go through,
Yeah.
I think we still have time.
yeah, sounds good. So I think this follow-up research on gentrification is similar to the mapping projects we did earlier. Instead, we find different signals instead of like buildings change, reconstructed, we find new construction of some sorts of businesses, like this is a very strong signals, visual cues of gentrification, like full service restaurant, new yoga studios neighborhoods. And we map them in 3 different cities. And we'd be able to find those gentrifying neighborhoods by spotting those gentrifying buildings. And yeah, so we benchmark with, so previously sociologists, they use like the number of permits and number of like the income level to predict how gentrified into neighborhoods, our measures have a higher correlation. And we also be able to locate some early gentrifying neighborhoods. I think in the adjacence of the gentrifying ones by spotting like the construction of new apartment buildings and things like that.
Is there any ground truth data for gentrification?
Yeah, so our collaborator Jacqueline Huang, and she has some previous studies, and she has some labels for gentrification based on census data. They have a formula based on income, based on demographics. They have this classification whether this neighborhood is gentrified.
They accept the truth. Kind of, yes.
Yeah, something like that. And yeah, so that was another very interesting study we did. Yeah, so we find that this built street view data to determine whether a neighborhood is gentrifying, but also serve as a warning system for policy design where we can detect some early signals for gentrification. Yeah, in summary, we go through this applications where we can not only detect how building recovered, but also how neighborhoods gentrified.
And
Yeah.
the gentrification study is based on all street view images in the cities you mentioned through how many years?
I think through 10 years.
Oh, wow, that is
Yes.
insane. You are rich in Google Street View.
Yes, yes. We build a pipeline to extract street view data, historical street view data from Google, and once you have an API from Google, you can actually download the street views. Yeah, it's cheaper than we thought, actually. Yeah. Yeah, I think that's all my presentations. I'm happy to take.
That's true.
Yeah.
Can you go back to 36 or 37?
Yeah.
You showed the score curve.
You can just type 36 and enter.
Yeah, perfect. Yeah, I was wondering, like, how sensitive these disparities are to the way that you model.
Yeah, great question. We actually did sensitivity studies on if we change it to 1.5 or change it to 1.1, the curve still remains roughly the same trend. It's just the level of the final point, like the final, whether the neighborhoods recovered to the pre-disaster status, the curve can be a little bit steeper or a little bit more smooth. Yeah, the trend's still the same, which is
Like the ordering is the same between the high.
yeah, exactly. The relative positions between like all the 3 income groups are still the same. So it means after the disaster, the disparity will actually be amplified between these groups.
And if you don't mind, a follow up, have you considered like maybe accounting for the speed of recovery as one of the model of score?
Yeah, that's also a great point. One of the limitation for Google Street View is they sample place like every 1 to 3 years. Sometimes in suburban areas, they sample them every 5 years. So we don't have the exact date for that building getting rebuilt. Sometimes we lag a little bit, so you can see the curve here actually have a sharper increase in the 5 years-ish after disaster. That's part of the reason is a lot of neighborhoods, they refresh their street view data at 5 years, like every 5 years. So we can actually observe the recovery at that period. We sort of make sure that our observation is long enough to 10, 12, 15 years after the disaster. We do know that this place is being rebuilt and it's being improved. So our final conclusion is still valid. But like the exact date and exact speed of how fast the buildings get recovered can be less accurate to track. Yes.
That's our question. Maybe,
Yeah.
Okay, yeah, thank you for letting me go first. I think the understanding I get from the modeling approach is that it depends a lot on the context.
Yeah.
Like, it's easy to tell if there's a new construction, but it's not that easy to tell if it's an improvement, as what Scott said, right? Like, the assessed value might be different from
Yeah.
like, just look at the image of the house.
Mhm.
And you have an example on greenery, right? Like, you show me that image, I don't know if there's greenery coverage, even it's hard for a human to define that. So I'm just wondering, like, do you think that there could be a uniform model or like a large or word model that actually handles all these different understandings of the level of details? Because I think like you train different models for different tasks.
Yeah.
But it's at the end of the day, they are processing information, imagery, and they're turning that into text and understandings. Do you think they're what do you think about the models?
Yeah, that's actually one of the frustrations we have, like after 24, after the studies, we find the curve of those large models increase a lot. So we don't need the specific models, we don't need a dedicated data sets to actually do tests like this. So today, if you input these questions to Claude or whatever frontier models, they did a pretty good job. So I believe like in the future, like one large models can actually be your experts in different domains. Like you don't need a dedicated model to answer questions like for building detection, the other model answer questions for change detection. Like a unified model can actually be, I think, be like an experts in all of those fields. They're training and they're evaluating on so many different tasks and they're evolving so quickly. So I think for this study, we directly used GPT-4o. It was around the end of 2023 when they first published their API. I think they're one of the first multi-model large language model APIs, and they already did a pretty good job in like classifying these tasks. I think if you use frontier model today, you will do a better job. So that's my.
How about for things that are a little bit more difficult to describe in language? Like it's easy to describe if something is constructed or not, or if there's greenery. Then it's pretty clear to the model what you want. But the improvement, right? Like that's pretty vague. Do you think the language model can also pick up what improvement actually implies within a particular context?
Yeah, we need to define what is improvement in the prompt. So when we do this task, we actually listed like foundation, like reinforcement, those sort of descriptions for improvement. You need to make it concrete, so language model will hallucinate less. Yeah.
Thanks.
Yeah.
Thank you. Can you go back to 36, please?
Yeah. So that.
So I have a bunch of questions that may be just one. So the first part would be like that lower income is pre-disaster, right? Like the way that you categorize in the disaster. And I was also wondering if you did this graph, if regionalized, like by regions, because I can see that there might be places where things look different. Because I was shocked about like lower income and higher
Yeah.
income, like they start at the same place post disaster. And I was thinking about New Orleans, where like the highlands are the rich people and the lowlands are the poor people. So Katrina was very disproportionately
Yeah.
affected. And then because of that, like also thinking about New Orleans and like trying to mix both of your projects, there was things that people like flew from New Orleans, and then some of them weren't able to come back to New Orleans, and those people were the ones in the lower income places, and the buildings, a lot of them were still in good shape.
Yeah.
But because there was a high rate of abandonment, they tore them down and built like gentrified buildings in places that were low income. So like I was like, this is the whole thing. Like these can change depending on when you label your neighborhood and where is that happening, like because of the infrastructure and where are things located.
Yeah.
And also like how gentrification happens after an event like this.
Yeah, I think great observation. And one thing is we normalize the recovery score for different incomes with pre-disaster. So we kind of use this same baseline for different income groups. And we see like we assume that for all these neighborhoods, they have a 100% built environment level. And how much percent left in years of recovery, things like that.
So this doesn't mean that they were effectively at the same rate, so like proportionally to what it was before they were these affected by these rates.
Yes, yeah.
Okay.
Question, so, which specific satellite did you use for your research?
Yeah, so satellites. We have, I think we have multiple sources from Google Earth. We have like Sentinel, we have Planet Labs. So Google search of Google Earth, they have a Google Earth engine. And once you query this coordinates, we query for the higher resolution possible for this place. And they have a mix of sources.
I see.
Yeah,
So you use whatever Google is.
yes, exactly.
Okay, oh, and do you ever find resolution to be a limitation for satellite imagery in your research?
Yeah, great question. So I think we filter out those very coarse resolution ones because for skyscraper data sets, we need to find like the features of that place, like the cotton farmland, like a solar farm that actually requires at least like 10-meter resolution or even more granular resolutions. So yeah, we drop the more like question, yeah.
And just one more question, have you considered, I know your research is focused on like East Coast and Texas region, but have you ever considered like investigating how wildfire is impacting the West Coast and how it's like impacting the rebuilding rate
Yeah,
through that different socioeconomic?
yeah, that's a great research idea, actually. We haven't done that yet. I think one of my lab mates, Zhe, he had a paper on wildfire. I think he also used street views to classify whether there's a power grid that is above the land or below the land on the ground. So if it's above, it's actually more vulnerable to wildfire. Like they have a higher risk of fire. If it's underground, it's less resilient. We have some study like that, but we haven't done like building recovery after wildfires. Not good, but that's a good. Yeah, last question.
Maybe I can, mine is like more of a like granular like data question, so maybe I can give it to you.
No, you get priority.
So. On Google Street View, there are a bunch of photos uploaded by, like, users as well as by Google. And so this like, post-fire question brought to my memory that in Altadena, after the Eaton fire, there's like been no photography since 2022. Whereas in the Pacific Palisades, some guy like drove around, and so there's like street view coverage post-fire for the entire burned area. And so I'm wondering if like you would have access in your data set to like
Yeah,
the photos that that guy took, as well as the street view column.
That's actually one of the reviewers asked us, what is the sampling bias of street views across regions? For some regions, especially, I think Google, they sample the areas based on the number of users in that area. For example, in San Francisco, there are a ton of users. They update their street views more than once per year. In like suburban areas, they do it maybe 5 years, every 5 years. Yeah, we validate that with satellite imagery to make sure that, like for satellites, you can sample anywhere. So you can still see the abandonment through the satellites. So we also calculate how much buildings are abandoned from satellites and sort of cross-validate that. But yeah, for the specific sources, we haven't checked that. So there's definitely more, some places are getting sampled more than other places. Yeah.
Thanks.
Thanks, Scott. I'd like you to ask the absolute last question and also help us to introduce our next speaker, Professor Jin.
Okay.
Yeah.
So I'm wondering on those recovery curves, have you tried to disaggregate by like state or county? I'm kind of curious if different local policies, like in how easy is it to permit, you know, new builds? Like, is that significant? Because politicians talk about, we're gonna make it easy to rebuild, we'll make it so, and I'm wondering if the data actually shows that communities do recover faster. Have you looked at that?
We haven't, actually a great point. So Jacqueline, she's a sociologist. She wanted to do a follow-up study on that, more policy focused. And yeah, there's definitely a regional divides in how to assist or how to permit buildings after disasters. And some places are more helpful than other places, I think. Yeah, that's a great future I think to explore.
No post on that. I think you know us.
So I can share.
Oh,
Yeah.
Okay.
Okay. I'll share.
We do not have seminar next week. We will resume in 2 weeks on Zoom. And it is a special one because we often feature early career researchers, but this time I think Professor Junjie Qin is kind of like mid-career or transition from early career to mid-career. So he also kindly agrees to share his own experience about this transition from a PhD student to postdoc and during his on his tenure track towards a tenured professor. Scott, do you want to add that?
Yeah, sure. So I think Tianyuan will
I will
put
share this.
the poster up in a second, but Professor Junjie Qin actually, I think is a alum of your same research group.
Yes.
But he's maybe associate professor now at Purdue University. And his background is in you know, optimization controls. He thinks about economics and markets quite a bit. But I asked if he would come and present because he's doing a lot of work right now on data centers and data center flexibility. So it turns out that Patty Poppy, the CEO of Pacific Gas and Electric, is an alum of Purdue. And Purdue's College of Engineering has created this big data center energy consortium. In our backyard, Purdue has made this connection with PG&E. So Junjie is doing really cool work in this area, and I was hoping he could share with us.
Yeah, so make sure you join us on Zoom in 2 weeks. Thank you very much for coming. See you.